I want you to picture a log. Not the padlock on your gym locker, not even the deadbolt on your front door. I want you to picture the lock that secures, well, pretty much everything else.
Invisible stuff.
Exactly. The internet, your bank, private messages, the entire digital economy. It's all guarded by this mathematical structure. And for decades, we've kind of assumed it works because it's random.
That is the standard view, yes. Security through chaos, basically. If the prime numbers are scattered enough, no one can guess the key.
But today, we are diving into a document that just says, you're looking at it all wrong. We're looking at a paper titled Deep Analysis of Arithmetic Recursion Chains and Knapsack RSA Hybrid Structures.
Which, let's be honest, is a title only a mother could love.
It is a mouthful.
Yeah.
And the original is German, Tiefen Analyse, which just makes it sound more intimidating. But the mission of this paper is, well, it's wild. It suggests these numbers aren't random dust. They're part of a rigid geometric map, a universal resonance code.
It's a fascinating premise. The source is arguing that the boundary between the code in your laptop, the rigid binary logic, and the code that runs the universe, like physics and nature, that boundary is blurring.
So today we're going to try to crack this code. We're going to find out why one number, 65,537, is the master key to the internet.
And we'll look at a 36-hour clock that acts like a kind of GPS for primes.
And we're going to see how a mathematical ghost called Negetz24 might just connect the Fibonacci sequence to the actual dimensions of reality.
It's a journey from the microchip in your phone all the way to the stars.
Let's dive in. I want to start with the star of the show, 65,537. To me, that just looks like a number. Why this one? Why not 7? Why not 1,000,000,003?
Well, to get the why, you have to look at the what. This isn't just any prime. It's what we call the fourth Fermat prime. Mathematically, it's 2 to the power of 2 to the power of 4 plus 1.
That is a lot of twos.
It is. But that specific structure gives it a very unique personality. If you write 65,537 in binary, zeros and ones, it's actually incredibly beautiful. It's a 1 followed by 15 zeros, then another 1.
So wait, 1, 0, 0, 0. It's a palindrome. It reads the same forwards and backwards.
It is. It's elegant. But in engineering, elegance almost always means efficiency. This number is the standard public exponents, the little e, for RSA encryption.
So almost every time I see that little padlock icon in my browser.
65,537 is doing the heavy lifting in the background, yeah.
But hold on, why does the binary look matter? Is that just like an aesthetic thing for coders?
No, it's all about raw speed. Think about how a computer calculates. Doubling a number is the easiest thing it can do. It's just shifting bits. Computationally, it's almost free.
Okay, so doubling is cheap.
Right. And because 65,537's binary form is almost all zeros, the computer uses this shortcut called square and multiply. To encrypt something with this key, the computer only has to do 16 squarings, which is just doubling the exponent, and one single multiplication.
Wait, walk me through that. Why do the zeros make it faster?
In binary math, every time you hit a 1, you have to perform a multiplication. Every time you hit a 0, you just square the previous result. So with its 2 1s and 16 zeros, you get 16 squarings and only one extra multiplication at the very end.
So it's the path of least resistance for the hardware.
Exactly. If you picked some other messy prime number, its binary code would be full of 1s. The processor would have to stop and multiply over and over. It would literally slow down the entire internet.
So 65,537 is the sweet spot. Fast, but also big enough to be secure.
It's robust. The source mentions this structure also minimizes hardware errors. When you're doing billions of transactions, you don't want a number that makes the processor sweat. You want what the source calls an oscillator.
An oscillator. That sounds like something you'd find in a radio.
That's the term they use. In this theory, we didn't just pick this number. It acts like a tuning fork. It stabilizes the frequency of all the encryption keys.
Okay, I get the efficiency part. But how do we even know it's prime? I mean, I'll take your word for it, but the source talks about a prime certificate. That sounds like a diploma hanging on a wall.
It's sort of like that. Usually proving a massive number is prime is really hard work. You run these brute force tests. But for 65,537, we can use something called the Lucas test.
Which is?
You just look at the number right before it, n minus 1. So 65,536. And that number is exactly 2 to the power of 16. It has only one prime factor, 2.
Cure.
Because its neighbor is so clean, verifying its prime status is incredibly simple. There's no ambiguity. And it goes beyond that, into the physical. Because it's a Fermat prime, you can theoretically construct a regular polygon with 65,537 sides.
With a ruler and a compass. A shape with 65,000 sides.
Theoretically, yes. Gauss proved it was possible. To our eyes, it would look like a perfect circle, but mathematically, it still has corners. It bridges that gap between a rough shape and a perfect one.
That's a connection between the digital and the geometric I hadn't even thought about. But let's zoom out. So we have our oscillator. But an oscillator needs something to resonate against. The source says these numbers don't just float in a void, they live on a map.
Right, and this is where you have to shift your perspective. We all think of the number line as this infinite straight road, right? 1, 2, 3, 4, forever.
Oh, we learned in first grade, yeah.
The source says, take that road and wrap it around a clock face. But instead of 12 hours, this clock has 36.
Why 36? That seems so arbitrary. Why not 10 or 100?
36 is what's called a highly composite number. It just plays nice with everything. It divides by 2, 3, 4, 6, 9, 12, 18. It connects to the 360 degrees of a circle. It harmonizes linear counting with cyclical rotation.
Okay, so we're on this 36-hour clock. How does that help us find primes?
It acts like a giant filter, a sieve. The source lays out a rule. All prime numbers, except for 2 and 3, must fall into one of only 12 specific lanes on this clock.
Hold on. There are 36 slots, but primes can only live in 12 of them.
Yes.
So you can immediately ignore 2/3 of the entire number line.
Exactly. Just think about it. If a number lands on lane 2, it means it's an even number, divisible by 2. So not a prime. If it lands on lane 3, it's divisible by 3. Not a prime.
So the only places primes can even hide are in the slots that don't share any factors with 36.
Precisely. The residues where the greatest common divisor is 1. So lane 1, lane 5, lane 7, and so on.
That is incredibly useful if you're hunting for giant primes.
It is. It's like you're searching for a fugitive's car, but you know for a fact they can only drive in the HOV lane. You just don't look at the rest of the highway.
But wait a minute. I have to play devil's advocate here. Just because a number is in lane 5, that doesn't guarantee it's prime, does it?
No. And that's the trick. The source calls numbers like 25 or 35 quasi-primes. I mean, take 25. It falls into a prime lane, but it's obviously 5 times 5.
It's an imposter.
The source argues they aren't imposters. They're structural markers. They mark the rhythm of the system. And this leads to a concept they call arithmetic spin.
Spin. That sounds like quantum physics again.
It's a very deliberate analogy. As numbers rotate through this 36 grid, they have an orientation, a positive or negative direction. The analysis suggests that number theory isn't some static list. It's a dynamic field of rotating vectors.
So it's like a GPS. If I know the spin and location of the factors, I can predict exactly where the product will land.
Right. It turns chaos into a clockwork mechanism.
Okay, I'm with you on the map. We've got the 12 lanes. But the source then takes this really weird turn. It starts talking about a heartbeat. And it points to this very specific, slightly negative number, minus 24.
This is where the math gets a little trippy. In our 36 modular clock, minus 24 is actually the same position as positive 12. It's the null point,
Right.
the system's axis of symmetry.
And the source connects this to the Fibonacci sequence.
It does. Now, everyone knows Fibonacci, right? 1, 1, 2, 3, 5, 8. Add the previous 2 to get the next one. Famous for describing everything from flower petals to galaxies.
Right, it just explodes outwards forever.
But the source applies something called digital root reduction to it.
Walk us through that. Sounds like a diet plan for math.
It's simpler than that.
Yep.
Take a Fibonacci number like 89, you add the digits. 8 plus 9 is 17, then add those. 1 plus 7 is 8. That's the digital root. You just keep adding until you get a single digit.
Okay, I'm with you.
If you do this for the entire infinite Fibonacci sequence, you don't get chaos, you get a perfect loop. The digital roots repeat in a cycle of exactly 24 steps.
A 24-step heartbeat hiding inside an infinite sequence.
Exactly. The source calls this the stabilizer. The Fibonacci sequence wants to expand forever, but this 24 cycle grounds it. It keeps it in sync with the 36 modular map we were just talking about.
And this is where the source drops the bomb.
Yeah.
It says this number, 24, isn't just about flower petals. It's about string theory.
It does. It references the Ramanujan summation. This is a famous, slightly mind-bending result where if you sum up all the natural numbers, 1 plus 2 plus 3 plus 4, on to infinity, the answer behaves like negative 1/12.
I've heard of this. It sounds completely wrong. Adding positive numbers gives you a negative fraction. That feels like a glitch in the simulation.
It's deeply unintuitive, but it's essential for the math of the universe to work, specifically in bosonic string theory. For the equations to balance, for the universe to not tear itself apart, the theory requires 26 dimensions.
26.
But 2 of those are light cone dimensions that cancel out. So you are left with 24 transverse dimensions.
So the source is claiming that this universal resonance code, this pattern in prime numbers, uses the residue of 24 to bridge the gap between our math and the universe's math.
Precisely. It claims Nagish-24 is the mechanism. It's the bridge between finite systems like our clock and the infinite series that describe the universe. It suggests primes fall into these patterns because they're following the curvature of those dimensions.
That is heavy. It implies that a secure server transaction and the vibration of a string in quantum physics are singing the same tune.
That is the core argument. Resonance.
Let's ground this again. So we have the oscillator, 65,537, the map, the 36 grid, the pulse, 24. But how do we prove this isn't all just a huge coincidence? The source brings in a detective story with a French mathematician from the 1700s.
Sophie Germain, one of the great unsung heroes of mathematics.
The source highlights this specific residue chain, minus 24, minus 43, minus 31, minus 127, minus 187. It just looks like a random list of coordinates.
It's not random at all. It's a lineage. Sophie Germain was working on Fermat's last theorem. She discovered the special class of prime numbers that now bear her name.
Sophie Germain primes. What makes them so special?
They come in pairs. A prime, let's call it P, is a Sophie Germain prime if 2 times P plus 1 is also a prime. They're linked.
Like a parent and a child.
Exactly. And the source outlines a law of resonance. It says if you have a Sophie Germain prime, it actually predicts the behavior of other numbers, specifically Mersenne numbers.
Those are the powers of 2 minus 1. Like 2 cubed minus 1 is 7.
Right. And the rule is this. If P is a Sophie Germain prime, then the other number, 2P plus 1, must divide the Mersenne number 2 to the P minus 1.
Can you give us a real example? Because
Okay.
when you say P and N, my eyes start to glaze over.
Of course. Let's use real numbers. Take 11. 11 is a Sophie Germain prime, so we double it and add 1. You get 23. The law says 23 must divide 2 to the power of 11 minus 1.
Which is?
2 to the 11 minus 1 is 2047. Guess what? 2047 divided by 23 is exactly 89.
It worked perfectly.
It works every single time. The source argues this is a causal link. It's not just numbers bumping into each other randomly. It's a gear system. You turn one gear, the other has to turn.
And that chain you mentioned ends at Nagna 187.
Yes. Minus 187 is interesting because it's 11 times 17. It's composite. The source calls this the termination point. It marks the boundary of that prime lane, the end of the line for that specific resonant frequency.
Okay, so we have this incredible map of reality. But the source isn't just admiring the view, it wants to build something with it. It talks about knapsack RSA hybrid systems.
This is where we leave the chalkboard and enter the server room. We all know RSA. It's secure because factoring huge numbers is incredibly hard.
Right, it would take a supercomputer millions of years.
But the source suggests combining it with the knapsack problem. Imagine you have a knapsack that can hold a specific weight and a pile of items with different weights. You have to figure out the perfect combination of items to fill the bag exactly.
That sounds like trying to pack for a low-cost airline.
If your packing list was MP hard, yes. It's a notoriously difficult problem for computers to solve because you basically have to try every single combination.
So they want to mash up RSA with this knapsack nightmare.
Exactly. But here is the genius part. They use arithmetic resonance to cheat. Well, to create a secret backdoor for the good guys. If you design the key using those 12 prime lanes we talked about, the authorized user who knows the resonance can solve the knapsack problem instantly. It's like they have a map showing how the items fit.
But the hacker...
The hacker doesn't know the resonance. To them, it just looks like a chaotic mess. They're stuck trying to solve the knapsack problem from scratch, which is computationally impossible.
So it weaponizes the structure of the number line itself against an attacker.
Precisely. And it also protects against things like lattice attacks or timing attacks because the keys are topologically rigid.
Rigid, I like that word.
It means the key fits into the geometry of the system like a puzzle piece. It's not just a password, it's a shape.
And this leads to the final and maybe wildest concept in the whole paper.
Yeah.
JADU-ASA and prime sonar.
Prime sonar is a beautiful image. They describe using a specific mathematical function to send out a ping into the number line.
Like a submarine pinging the ocean floor to map it out.
Yes. And by listening to the echo, which corresponds to the zeros of the Riemann zeta function, they can actually visualize where the primes are hiding. They call it navigating the solution landscape.
And the source claims this could be the key to quantum error correction.
This is huge for quantum computing. Quantum data is incredibly fragile. You look at it wrong and it collapses. But this source views the vacuum of space as an arithmetic string net condensate.
A string that condensate.
It means space isn't empty. It's a woven net of values. If your data aligns with this net, if it has that topological rigidity, then a small error doesn't matter. The system is self-correcting.
Because you can't have a slightly wrong prime in this system. It either fits the resonance or just doesn't exist.
Exactly. The error breaks the key immediately and alerts the system. It's the ultimate security protocol built right into the fabric of the universe.
This has been intense.
It's a lot to process for sure.
But let's try to pull it all together. We started with a single number, 65,537.
The oscillator, the steady hum that keeps the internet running.
We mapped it onto a 36-hour clock.
The map, the filter that shows us where primes are allowed to exist.
We found the heartbeat in the number -24.
The bridge, connecting our digital roots to the dimensions of string theory.
And we saw the chain of Sophie Germain primes acting as the gears in the machine.
The symphony of resonance.
That's the phrase from the paper that sticks with me. Symphony. The source is basically arguing that the universe isn't just noise, it's music. And we've just been looking at the sheet music upside down this whole time.
And once we learn to read it properly, things like cryptography, quantum computing, maybe even physics itself could look very, very different.
The source leaves us with one final concept: geometric residues. The idea that even when a dimension collapses, like when a 3D object becomes a 2D shadow, the information isn't lost. It's still there, hidden in the math.
Like a fingerprint.
So if the universe really is this arithmetic net, are we just resonant frequencies vibrating within those 12 lanes? And what happens when we finally figure out how to play the instrument?
That is the ultimate question, isn't it?
Something to think about the next time you see that little lock icon on your screen. Thanks for taking the deep dive with us. We'll catch you in the next lane.